Alright, so let's get settled down. Assalamu alaikum. So in the previous lecture we finished off by with an example of a Fourier integral. We had a function f of k, capital F of k, which tells us which waves do we want to add. We would like to add waves ranging from a wave number of minus k naught to plus k naught, and we were able to find the inverse Fourier integral or the function fx, and that function was given by some c sine of 2 k naught x divided by 2 k naught x, where c is some constant. So I gave you as a homework a question in which I asked how would you plot this function, or what would this function look like. Has anyone made a plot? दिखाइए. Good. Very good. Anyone else? Are there only 4 students in the class who? Okay. But the function is two-way. X could be negative as well. No, but x, the horizontal axis could go the other side. It's slightly confusing. Why do you have a straight line and then a hump?
Because sine of x is approximately equal to x.
No. ये मोबाइल फोन के साथ खेलना छोड़ दें. क्लासरूम में आप बैठी हुई हैं, घर पर नहीं हैं आप. Anyone else? ठीक. All right. So, as expected, the majority of the class has not been able to plot this function. So, let's start off by looking at how do we plot this function. So, could you make a plot of sine 2 k naught x? Plot sine 2 k naught x versus x. जल्दी करें प्लीज. Plot the numerator. You see, x can be positive or negative, so make two-sided graphs. All of you are used to making one-sided graphs, but x can be positive or negative. Make two-sided graphs. So this is my x-axis. I would like to plot sine 2 k naught x. It will look like this. This is a plot of the numerator. Very easy. Now I would like you to plot the denominator. I would like you to plot 1 over x. Can you please plot 1 over x or 1 over 2 k naught x on the same graph? x is negative. Is 1 over x positive?
When x is negative, 1 over x is negative.
Negative. So this should be on the other side. So our graph for 1 over x looks like this. So this is the graph of 1 over x. So now how do we find the graph of sine 2k naught x divided by 2k naught x? We multiply these graphs, because we have a graph of the sine function of the numerator and we have a graph of 1 over the denominator. So in order to plot this function as a whole, we would like to multiply the green graph with the yellow graph, and we would like to do a point by point multiplication. So could you plot what the result would look like? And remember, what's the value of 1 over x at x equals 0? It's infinity. This graph is going to infinity. And what's the value of the numerator? It's 0. So at x equals 0, you have 0 over infinity. This is undefined. So you would have to look at the limiting value and apply L'Hopital's rule. The value of this function at x equals 0 has to be equal to 1. Have you studied limits? Alright. So the value of this function, numerator over the denominator at x equals 0 is 1. You have to take the derivative of the numerator divided by the derivative of the denominator and put x equals 0. You will get 1. So the value of this function at 0 is 1. So now could you plot the product of these graphs, please? साइड लोब्स बहुत बड़ी बनाई हैं आपने, नहीं दरमियान वाली लोब बड़ी होगी, बाकी बिल्कुल छोटी लोब्स होंगी. गुड.
So in the last class, so you wrote sin k naught x over k naught x, but now you're writing sin 2k naught x. We derived the.
What did we derive in the last?
Sin k naught x over k naught.
Sin k naught x. Okay. This is k naught x. नहीं पता चल रहा. यार ये वाले लोब्स ना बहुत बड़े बने होंगे, छोटे होंगे. And on the other side?
नीचे की तरफ होगा on the other.
X and sine of k naught x divided by k naught x. The solution is so what is the solution? What does it physically represent? Alright, it's damping, but what is fx here in the context of waves? This is the wave. This is the wave in the real space. This is how the wave will look like if we start off with component waves whose wave numbers range continuously from minus k naught to plus k naught, and all of these have the same amplitude. You add up all of these waves, this is your resultant wave. Okay? So this is your fx, and if I would like to plot f of k here, which is the Fourier integral, the Fourier integral looks like this. And what this physically means is that you take a wave of wave number minus k naught, you add to it another wave of a wave number minus k naught plus delta k, you take another wave of wave number minus k naught plus 2 delta k, and you add up an infinitely large number of waves, and you go all the way up to plus k naught, and the number of these component waves is infinite because delta k approaches 0. It becomes infinitesimally small, and that is what is meant by saying that you have a continuous distribution of k values. All of these waves add up, and the resultant of these waves will give you this wave. So these are the component waves, and they compose, they add up, constructively and destructively interfere to give you finally this waveform. And this looks like a pulse, and it is traveling forward with a certain velocity. Now what is the width of this pulse? If I define this width to be delta x, the pulse in the real space has a certain width. Can you find out what the value of delta x would be? It's simple trigonometry, there's no modern physics involved here. Can you find delta x, please? What's the width of this central lobe? I mean the width along the horizontal axis. What's the difference in the values of x between this minimum and this minimum? Pi? Pi? So what's the value of x here? What's the value of x here? It's pi? 2 pi by? It's pi by k naught, right? The value of x here is pi by k naught, because then the numerator will go to 0. If x is pi by k naught, you get sine pi, which is 0. And what's the value of x here? Minus pi by k naught. So what's the value of delta x? 2 pi by k naught. And what's the value of delta k? What's this width equal to? Delta k is 2k naught. So what's the product of these two variables? Delta x multiplied with delta k gives you 4 pi. And this is once again the uncertainty principle. I gave you one example in the previous lecture. Here's another example. You add waves with a range of k values, you get a wave in space. If you want to increase delta x, you want to make this pulse go wider, you have to shrink this. If you would like this pulse to become tighter, you would have to expand this. So whatever I've said, I can show it diagrammatically. if I would like to plot the wave function or the pulse or the wave corresponding to this distribution of k values, I will get a pulse that is extremely sharp. Now if I narrow the range of k values, that is I add component waves with the smaller spread of k values, with the smaller spread of spatial frequencies, this pulse widens in the real space, because there is an inverse relationship between this width and this width. So this pulse will become wider. This will become even wider. And this will become even wider. So this is the uncertainty principle, G. I'm not concerned about the height so far. If this height remains constant, then this height is constantly going up. So that is determined by the value of C. C also depends upon K naught. So do you understand what all of this means? Because we have this relationship. If delta K goes down, delta X must go up. If delta K goes up, delta X must go down. So if you would like to make a pulse that is sharp in the real space, you would have to add up a large number of waves with component waves with a large spread of K values. Now this can also be time. If this is time here, then there's really no difference. This will become frequency, omega. And this will become f of omega, a function of frequency. So if I would like to have a very sharp pulse in time, very sharp pulse in time, I would like to add up a large number of frequencies. If I would like to have a broad pulse in time, I would only like to add a very short range of frequencies. So there is an inverse relationship between conjugate variables, between x and k, and between time and the frequency. So this is your first encounter with the uncertainty principle, and we have not invoked any quantum mechanics so far. So the uncertainty principle is a purely wave phenomenon to begin with. G.
Is the height same in all of these classes?
I've already answered that question. The height is not the same. The height depends upon C. If this height is the same, then this height will go up. So C also depends upon K naught. The height will not be the same. Right in the last row, G, आप थोड़ा सा मुझे बता सकते हैं, can you summarize what I've said and what all of this actually means? Can you please summarize? So in the next row, could anyone tell me what this physically means in the context of waves? उन्होंने mathematically बता दिया, wave की जुबान में इसका क्या मतलब है? And vice versa. ठीक है? So this is the uncertainty principle. It arises because of the wave nature. And the Fourier integral gives you the liberty of having a function in space or a function in the K space. K space means which wave numbers would you like to add to get this wave. So the wave is not necessarily a sine wave, it could be a pulse or a packet like this. Okay, we can construct wave packets, whatever wave packets our heart desires, no problem. You just have to choose the proper distribution function, and that distribution function comes from the Fourier integral. So next week the recitations will have probably 1 or 2 questions on the Fourier integral as well. So what I would now like to give you an example is We have to be really fast because we have to cover a lot of ground and I have to show you a demonstration as well. I would like to spend 10 to 15 minutes on the concept of phase and group velocities. Yellow chalk दे दें. Alright, so we know that the phase velocity is given by omega over k, and the other day we also defined a group velocity Vg, which is given by delta omega over delta k. Now if delta omega is very small and delta k is very small, you can write this as d omega over dk. So this is the group velocity of a wave packet. Now let me give you one example. Example number 1. And this will illustrate what the group and the wave velocity means. Suppose you have a prism. It's a glass prism. And white light comes into the prism. Suppose this incoming light is a mixture of red and blue. Now what's going to happen? बताइए क्या होगा? The two component waves will disperse. They will take different paths in the glass. So one wave will go like this, the other wave will go like this, and then they will refract, and they will refract differently, and then this wave will come out like this and the other wave will come out like this. So we have resolved the incoming light into two components, and which of these is red and which one is blue? The top one is red, this one is red, this one is blue. That is alright. So what does this mean in terms of velocities of red and blue, of the red and blue waves? So there's a red wave, which means it has a certain frequency, a certain wavelength. There's a blue wave, a blue component, which has a certain frequency, a certain wavelength. What does it mean in terms of the velocities of these waves? Which one has the higher velocity? Blue. Blue will have the higher velocity. And what velocity are we talking about here? We're talking about the phase velocity. So what we have is the phase velocity of blue is given by C divided by the refractive index for blue. Correct? And the phase velocity for red will be given by C divided by the refractive index for red. So the phase velocities are different. And which one of these has the higher wavelength? The longer wavelength? The red has the longer wavelength. So the phase velocity is inversely proportional to the wavelength. This has a shorter wavelength, a higher frequency, it has a higher velocity. So the phase velocity is given by some constant divided by the wavelength. Okay? Higher the wavelength, smaller will be the velocity. I can also write this as 2 pi over lambda A over 2 pi, which means A over 2 pi into K. Okay? This is the phase velocity. Fine? So the phase velocity is directly proportional to the wave number. I also have the relationship, we already derived that when we were looking at the wave equation, omega equals Vpk. Okay, we have this relationship from the wave equation. Now what I would like to find is the group velocity given by d omega over dk. And this group velocity is found at the central value of k naught. So we have two k's here. One is the k for red and one is the k for blue. K is just inversely proportional to the wavelength. So we have a k for red and we have a k for the blue. And the average value is given by k naught. So we compute this derivative at the average value, which is k naught. So what we would like to do, we would like to find out the group velocity, Vg. This will be given by d omega over dk, computed at k naught. Now, omega is given by Vpk, computed at k naught. I differentiate this. First, I differentiate dVp, dk, multiply by k at k naught. Then I keep Vp constant and differentiate k, which is 1, and I compute this at k naught. Now what is this derivative equal to? I would like to find this derivative, but Vp is dependent on k like this, so dVp divided by dk will be given by a over 2 pi. So this number is a over 2 pi multiplied by k evaluated at k naught plus Vp. Now what is Vp at k naught? Vp is just a over 2 pi times k naught. So this is my group velocity. 2 times a over 2 pi k naught. I've just done mathematics. Now what does the physics mean? The physics means I have a blue wave and a red wave. Each one of these waves has a certain wavelength. Now when I pass this kind of light through through the prism, do you actually see if the blue wave has a higher velocity? Do you actually see the blue light coming out of the prism before the red light comes out of the prism? No, you don't. So what is happening is there is a packet. There is a packet of light which is composed of two component waves that is entering the prism, and this packet of light inside the prism is moving not with the velocity Vp, it's moving with the velocity Vg, which is the velocity of the envelope, the group velocity. Even though the blue and the red lights that make up the wave, that are components of the wave, each one of them could be traveling with a different speed, but the resultant, which is a packet, is moving with the speed Vg, and that Vg is given by this value, 2 times a over 2 pi k naught, where k naught is the average k value for the red and the blue vectors, the red and the blue lights. So this was the first example I would like to give. The second example is quite exotic, and that example deals with fast and slow light. G. How I got what? How did I add? I would like to find the derivative of this. Okay? So this is a variable, this is a variable. First I differentiate Vp, multiply it with the variable I am not differentiating against. Then I write Vp and dk over dk. So I am just applying what is called the product rule of derivatives. All right. So a very interesting example of slow and fast light. We know that the group velocity is given by d omega over dk. And the phase velocity is given by c over n. And we also know that Kc is n omega. Omega is kVp, right? We know omega is kVp. G. No, it doesn't come out later, because what happens is that the red and blue light, the red and the blue light, they are moving in the form of a wave packet, and that wave packet is moving forward with the velocity group called the group velocity, and that group velocity is different from if you just put red light into it or just put blue light into it. If you just put red light into it, the group velocity of the combination of red and blue is double the speed of just red light, and the group velocity of is double the speed if you just put blue light. I have a simulation that will bring home this idea in a better way. Okay? So you know this relationship, fine. This relationship is just this relationship. This relationship, the phase velocity is c divided by the refractive index. This is how you define the refractive index. And you have this relationship. Omega is k over Vp. K times Vp. And Vp is given by c over n. Which means k is n omega over c. I'm just doing some jugglery with the variables because I would like to simplify the problem a little bit. So after these acrobatics, k becomes equal to n omega over c. This is the refractive index, this is the frequency, this is the speed of light in vacuum. Now what I would like to do is find dk over d omega. Let's find dk over d omega. C is a constant. Dk over d omega becomes the derivative of this. I get dn over d omega, omega plus n. One over c omega dn over d omega plus n. But what is this? Is this equal to the inverse of the group velocity? Yes. It is nothing but the inverse of the group velocity because it's dk over d omega. So what my Vg is c over n plus omega dn over d omega. This is my group velocity. So I have lights of different frequencies. The refractive index is depending on the frequency because the red and the blue light, they are bent, which means they have different phase velocities, which means they have different refractive indexes. So n is depending upon omega, and the relationship between the group velocity and this term dn over d omega is given in the following form. You must be lost, but this is all really simple algebra that I am doing so far. This is the most algebraic class of this course probably. But this has a lot of implications, and let me show you what the implications of this result are. let's concentrate on this term, dn over d omega. Does the refractive index depend upon frequency? Yes, normally it does. So if I plot omega here and I plot dn over d omega here, if I obtain a straight line, what does this mean? What is the meaning of this line? There is no dispersion. The refractive index is not depending upon frequency. All waves are moving through the medium with the same phase velocity. Okay? This is what this graph means. So this is no dispersion. Now what does this mean? There is dispersion. dn over d omega, oh sorry, I'm plotting n versus omega. I'm plotting n versus omega. So this means n does not depend upon omega, no dispersion, and this white graph means n is depending on omega. So there is dispersion. And what's the slope? Is it positive or negative? It's positive. So dn over d omega is positive. This is called normal dispersion. And if I have a situation like this, in which as the frequency goes up, the refractive index goes down, this is dn over d omega is now negative. This is called anomalous dispersion. Now if you look at this relationship, what I would really like to do now is I would like to plot, you see, remember we only talk about three things: words, pictures and equations. So I'm drawing pictures. So you should be really very good at understanding what these pictures mean. I'm drawing another graph. On the x-axis, I'm taking omega dn over d omega, and here I take the group velocity. So I have a pulse of light which comprises different frequencies. ठीक है, इसमें बहुत सी फ्रीक्वेंसीज हैं और हर फ्रीक्वेंसी और फ्रीक्वेंसीज का कोई डिस्पर्शन रिलेशनशिप है. ठीक है, डिफरेंट फ्रीक्वेंसीज पास थ्रू द मीडियम विद डिफरेंट वेलोसिटीज. नाउ व्हाट आई वुड लाइक टू प्लॉट इज दैट दिस पल्स, how does its group velocity change with the value, with this value? So what's the value of Vg when omega dn over d omega is 0? It's c over n, and c over n is just a kind of phase velocity. And what value of n do we need to choose? We choose the refractive index corresponding to the average frequency, okay, or the refractive index corresponding to the average wave number, because this has to be some average. Omega is dependent upon n, so what n do we choose? We take the average omega and find its n. So this curve has a height c over n when omega dn over d omega is 0. And what happens when this value goes up? When this value increases, what happens to the group velocity? It decreases hyperbolically, like this, right? It goes down. So the group velocity keeps on decreasing if we increase omega and if we increase dn over d omega. We are assuming that dn over d omega is positive, so we are assuming normal dispersion. So if this number goes up, Vg goes down. If this goes up, Vg goes down, like this. When omega is 0, the height is c over n. And can this group velocity actually go higher than c over n?
value becomes negative.
Why not?
If only if the gradient.
Only if this dn over d omega becomes negative can the group velocity go higher than c over n. That is anomalous dispersion. So this curve can go like this. And what's the value, what's the abscissa here? What's the value of this variable at this point? Minus n, right? Because when this number is equal to minus n, Vg goes to infinity. So in this region, what we have is normal dispersion. Normal dispersion means the group velocity is smaller than c over n. Okay, which means that the pulse gets slower in the medium. The pulse gets slower in the medium. And for anomalous dispersion, this is the anomalous region. In the anomalous region, the pulse actually becomes faster in the medium, because the group velocity has now gone beyond c over n. So what this means is, by properly choosing the value of dn over d omega, by choosing it to be positive or negative, by choosing between normal and anomalous dispersion, you can have two regimes. One is the regime of slow light. You can slow down light. So light in vacuum has a speed of 3 into 10 raised to power 8 meters per second. For normal dispersion, the pulse of light travels slower in a medium. For example, it can travel at 100,000 kilometers per hour. It can travel at even slower speeds, at 100 kilometers per hour, just like when we are driving on the motorway. It can even travel at exceedingly small speeds. So I'm walking like this, light can travel with me. So slow. If we increase dn over d omega by a large amount, if this slope becomes very large, which means that the refractive index changes suddenly with the frequency, you can achieve slow light. In fact, you can make light go so slow that you can even make light come to a halt in certain mediums. It can even stop, and you can have trapped light. And what we are looking at is not the phase velocity, rather we are looking at the group velocity of a pulse of light. In this regime, which is the anomalous regime, in which dn over d omega is negative, can you achieve velocities greater than the speed of light in vacuum? So what the special relativity says is that the phase velocity cannot be greater than the speed of light. It's absolutely 3 into 10 raised to power 8 meters per second. That's the phase velocity. But it does not put any restriction on the group velocity. The group velocity can be much higher than the speed of light. So you can have slow light, you can have halted light, you can put brakes on light, and you can make light go faster through certain mediums under certain conditions and achieve superluminal communication, because it is the group that is carrying information. So the phase velocity has an upper limit of c or c over n in certain media, but the group velocity can go beyond c over n. So what does the group velocity and the phase velocity actually look like? I would like to show you a simulation on the multimedia. Remember, if you go home and don't look at this material again, you'll forget, because this is mathematically it's simple. Mathematically the algebra is straightforward, but what is difficult is the concept, because the concepts are counterintuitive. So unless you go home and don't look at this material again, you'll be flabbergasted, you'll not understand. Alright, so normal dispersion. I've also uploaded these simulations on our website. Zara baatein please na karen. Ahmed, lights please band kar de sari. Alright, so what you're seeing here are two component waves. This is one wave and this is the other wave, and you're taking the resultant of these waves. So the two individual waves are traveling waves. This is a traveling wave, this is a traveling wave, and they have different frequencies, different values of omega and different values of k, and you're adding these waves. So this is what we did in the first lecture on waves. We added two component waves and we found a resultant wave. So the resultant wave in this case is looking like this. So I can increase one of the frequencies. See, I'm getting a beat-like pattern. I can get a beat-like pattern. So now what's happening is that this envelope on its own is moving with a certain velocity, which is called the group velocity, whereas the individual waves, they are moving with their respective phase velocities. So this represents normal dispersion. This simulation is made for normal dispersion, in which the refractive index increases with an increase in the frequency. So I can change the speed of the component waves. This is a better looking simulation. Now observe an envelope. The envelope is moving in one particular direction. It appears to be moving in one direction, and the envelope is moving with the group velocity. See, I increase the speeds of one of the waves, the envelope changes, the group velocity changes. So this is normal dispersion. This is a simulation for normal dispersion. I can also have anomalous dispersion. So there's an envelope that is moving with a certain velocity in a particular direction. In fact, let me tell you, there's an error in the simulation that these guys have made. This is actually normal dispersion. The previous example was for anomalous dispersion. This is normal dispersion because the envelope is moving in the forward direction. This is normal dispersion. There's an error these guys have made in making this naming this simulation. This is normal dispersion because the envelope is moving in the forward direction. This is forward propagating light. The previous example, the envelopes were moving in the backward direction. That appears to be backward moving light. I can also have no dispersion, in which the refractive index does not change with the frequency. So this is what I get. Now this is an example in which this second wave has a slightly higher frequency than the first wave. Alright, and the two are now currently set at the same phase velocities. So speed 1 equals speed 2. If I increase speed 1 a little bit, I notice that this envelope starts moving with a certain velocity. So the velocity of the envelope is the group velocity, whereas the velocities of the component waves, that's the phase velocity. Now there's an example of group velocity with anomalous dispersion. Now you observe that the envelope is moving at a much higher speed than the speed of each of the individual waves. This means that the group velocity is higher than the phase velocities. And this is what happens in anomalous dispersion. So these are examples that I've uploaded on the website. I can have zero group velocity. The group velocity can be made to be equal to 0. And here you observe that this envelope remains where it is. The height of this envelope remains where it is. So I can adjust the dispersion relationship dn over d omega such that the group velocity is almost 0. That represents dn over d omega equals infinity. You change the frequency a little bit, the refractive index changes by a very large amount. And this means that a pulse that is charged into light, that is charged into a medium, remains where it is, or information is stored inside the medium. You're trapping light inside the medium. ठीक है? यहाँ पे आप देखो ये envelope अपनी position change नहीं कर रही. This is like a standing wave. So by just tuning the dispersion relationship, you can control what the group velocity is going to be. Last, you can have a negative group velocity. Here you observe the envelope is moving in the opposite direction. This represents light that is moving backwards. So you have two media. You have a medium and vacuum. You put light into vacuum and wait at the other end. It comes out at a certain time. But you take a medium which has this kind of dispersion relationship. You put light into this medium, the light will come out of this medium before it would come out through vacuum of the same length. This is what is meant by backward moving light.
How do you control such a medium?
Alright? So how do you control such a medium? These mediums are actually engineered. There are elaborate procedures to make such mediums. So what you really want is a control over dn over d omega. So what you can do is you can make mediums omega dn over d omega. बहुत खुशी हो रही है आपको ये देख के, ये सिमुलेशंस, मुझे भी बड़ी खुशी हुई थी. तो ऐसे मीडियम्स इंजीनियर किए जा सकते हैं, यानी बनाए जा सकते हैं. ठीक, इन्हें कहते हैं मेटा मटेरियल्स. और इन मटेरियल्स का एक खास डिस्पर्शन रिलेशनशिप होगा which looks like this. At a certain frequency, the components of the medium, which are basically oscillators, they resonate with the incoming light. And when they resonate with the incoming light, they have a dispersion relationship like this. They absorb light, and they're just like a harmonic oscillator which is being forced by an external function. It will have a certain resonant frequency, and when it has a resonant frequency, the change in the refractive index with omega looks like this. So this is the region. This region is the normal dispersion region. This region is also the normal dispersion region because the slope is positive here and the slope is positive here. But this region is the anomalous dispersion region. So if you put light with the frequency in this range into such a medium, you can have anomalous dispersion and you can make light go faster. The group velocity can actually be faster. So you can have so-called backward propagating light. Light that appears to move backwards. But it's not light that is moving backward, it's the envelopes that are moving backwards.
So if you can have light, if we can have faster than moving light, so why don't we have communication that's faster than light?
Because these mediums have to be made in large, they have to be drawn out into wires or optical fibers which are very long, and you can have superluminal communication at, say, of the order of micrometers, yes, but it's difficult to make these materials technologically.
What is no dispersion again when there's
What is?
no dispersion? What is it?
When there is no dispersion, the refractive index or the phase velocity does not depend upon what color of light or what wavelength of light you're putting into the medium. So in some cases you would like mediums that have no dispersion. You would not like the light to disperse. You would like, so you can engineer such materials as well. You can dope normal materials with compensating dopants so that the dispersion is counteracted and you can get normal dispersion or no dispersion materials. So I have a demonstration. We just have 15 minutes since a lot of hard work has gone into this, and Rabia and Ahmed have done some work, so I don't want to miss this opportunity to present a brief demonstration. So what we really have, what are we doing in the previous two lectures? We've seen that waves have certain characteristics, that waves can add and subtract, and we've also seen the concept of phase and group velocity. So now what I would like to show you is the most important example that radiation is made up of waves. And whenever we have wave motion, we know that the phenomenon of interference takes place. That is, waves constructively and destructively interfere. So I have one or two demonstrations which actually show you diffraction patterns or interference patterns from a double slit and a single slit. So if you can please zoom in onto the equipment, but you have to sit down so that lights are off. थोड़ी सी एक ये लाइट जला सकते हैं, ये वाली. ठीक है, ठीक है. So what we have here is a laser. Now this is a laser tube. This laser tube comprises a mixture of helium and neon. So it's a gas laser. Helium has quantized levels, neon has quantized levels, and you can optically pump these atoms to achieve population inversion. You apply a high voltage with the help of a power supply that is here. Right? This is a power supply. This is applying power to this tube, the laser tube, and it's giving out light. And I also have a double slit pattern. What the double slit pattern is like, if I look really closely enough, Ahmed, usko dekho. So it doesn't appear in the camera very properly, but these are in fact two slits. So this is a razor blade which has been cut into two halves, and those halves have been placed back to back, and inside the opening Rabia has placed a needle, so or a pin, like a paper pin, or so we have two slits. It's not really visible in the camera, but this is actually what we have. So we turn on the laser. Now the laser should not go into your eyes. Ahmed?
Okay.
So I switch on the laser. Okay. अब आप इस पे focus कर लें. So this is the laser spot, red laser, 633 nanometers. Okay. So I try to place this slit. अभी ना करना था, मुझे देख लूँ. लाइट जरा ऑफ कर, जूम आउट करो सर. अहमद जूम आउट करो. All right. So this is the famous double slit pattern that you've seen in your A levels. So what we have here is a central maximum. There is no need to, I didn't invent this. This was invented 200 years ago. So what we are seeing here is a central fringe with the maximum brightness, and then there's a dark area. You see this dark area? No light reaches here. So there's something that is telling the light not to go there, and that is destructive interference. Light, the individual rays, they are reaching here, but they are all out of phase. They are differing by half wavelengths. So as the resultant wave that is reaching these dark regions is zero. There is no resultant wave that is reaching these dark regions. So here is a dark band, then there's a dark band, a dark band, a dark band, a dark band, and we see the same pattern repeating on the other side. So ideally the double slit interference pattern should be equal brightness, bright and dark fringes, bright and dark fringes, bright and dark fringes. But there are reasons, there are mathematical reasons because of which they're not of the same brightness, all the fringes. And this has to do with the single slit diffraction pattern. So this is a vivid example of, or a vivid proof that radiation or light, in this case 633 nanometers laser light that is coming out from a laser, comprises waves, and these waves interfere. They can interfere constructively, they can interfere destructively. Now I'm going to show you the second So this is actually doing physics with a razor blade. So let me show you the second example, and that is of a single slit. All right. So this is a single slit diffraction pattern, and here you observe that there is a central maximum, and then the brightness wanes off. It decreases as you go away from the central maximum. So you can have diffraction from a single slit, you can have diffraction from 2 slits, you can have diffraction from 3 slits. And we'll start off the next class with actually a 5-minute theoretical understanding. The class is not yet finished, remember, just wait, we have 5 minutes to go. So the third demonstration I would like to show you is with a grating. Let me first finish please, then I'll answer your questions. लेकिन आप खामोशी से तो सुने ना, मैं आपको डिफरेंस आपको विजुअली नजर नहीं आ रहा, मैं आपको मैथमेटिकली अभी दिखाऊंगा, ठीक है? Sabieh, can you show the, इसको दिखा लें. इस पे फोकस करो. अच्छा. ये सारा है. चलो ठीक है, बस इसको वैसे दिखा. So in this example we have Ali, आप उनको भी देख लें सही. Ali, in this example we have a grating which has effectively a very large number of slits in a small interval of length. So what we observe here are discrete spots of light which are spaced at a certain interval, and there is hardly anything in between, and there will be one spot here, one spot here, there will be other spots as well at different distances. So light is trying to reach the area between these spots, but really destructive interference is taking place. So all the waves destructively interfere, and the resultant intensity that reaches in the region in between these points is actually zero. Now we can do some quantitative analysis as well, and I will just like to give you a flavor of the kind of quantitative reasoning that is required in order to understand these diffraction patterns. First of all, I would like to show you a photograph of a single slit pattern that was previously taken in the lab. You can see this single slit pattern. So there is a variation in the brightness as we go from the central lobe to the left and to the right. देखो ये सेंट्रल लोब है, और उसके बाद आपकी ब्राइटनेस इवेंचुअली कम होती जा रही है as you go away from the central lobe, and there are bright and dark spots. So one can actually do a more careful analysis of this diffraction pattern. So we have a software called ImageJ, which is actually used it's a very popular software amongst biologists especially. So we can find a plot profile, and this is what the plot profile looks like. So the plot profile is the variation of the intensity versus the line I drew, and that line is the horizontal axis. So we have a central lobe, a very strong lobe. It's very sharp. It's not sharp, but it's very high. The amplitude is very high here. And then we have fringes. We have a dark region and a bright region, a dark region and a bright region, bright, dark, bright, dark, bright, dark, bright, dark. So these are the interference fringes that we observe from a single slit. Likewise, we can also look at the fringes from a double slit. And we can do a more careful analysis as well. So this is the double slit interference pattern, and of course there are some visible differences which have to be looked at from the perspective of theory. But let me give you a very brief overview of just 2 minutes, which will be a nice closure to this lecture, of what single and double slit interference actually means. If you just have a single slit and wave fronts of light come in, and then you have a screen, what you observe in the single slit case is a central maximum followed by fringes that decrease in their brightness. This is the pattern of a single slit. If instead of a single slit you had two slits, and you had wave fronts of light coming in, first of all, if I suppose that no diffraction takes place, suppose no diffraction took place, then the wave fronts would issue out from these slits in this fashion, and you will really not observe any diffraction pattern. You will just observe two lobes like this. Remember the first class, but you don't see this. What you actually see, ideally what you should see a central maximum and then an equal brightness, equal darkness fringe pattern. But you're not seeing this in reality, because what you are seeing is this slit is really a single slit as well, and this slit is also a single slit. So you're not seeing a double slit pattern, you're seeing a combination of two single slit patterns. So you would have to take a double slit pattern and multiply it with a single slit pattern. Eventually what you will observe are fringes like this in the double slit case. So summary. For the summary, let's make a table. It's very important to keep an eye on the panoramic view. We have matter, we have radiation. Just half a minute. We have wave and we have a particle. What we've seen so far is that matter has a particulate existence and radiation has a wave existence. And tomorrow we're going to explore the particle nature of radiation, and in the end we'll look at the wave nature of matter. And this is what we'll cover before the midterms. Thank you very much.